We start a new module, microwave resonators. In this module, we cover the following contents. First, we discuss series and parallel resonant circuits, conventional circuits. Then we discuss Q factor, both unloaded and loaded Q factor. We discuss about the bandwidth of such circuits. Then we also cover transmission line resonators, and finally we discuss waveguide resonators. So, a resonator is a device or circuit that exhibits resonance. In an electrical circuit, resonance condition occurs at a frequency when the capacitive and inductive reactances become equal in magnitude and electrical energy oscillates between electric field of a capacitor and magnetic field of an inductor. Microwave resonators are used in a variety of applications. For example, filters, oscillators, tuned amplifiers, frequency meters. These are some of the examples where microwave frequency resonators are used. Now, at frequencies near resonance, a microwave resonator can be modeled as series or parallel RLC lumped element circuit. Therefore, the basic properties of series and parallel RLC circuits are reviewed first. So, we consider series RLC circuit, and for the series RLC circuit shown in the figure, we can write Zin is equal to R plus j omega L minus j 1 by omega c, and then we can write Zin equal to R plus j omega L into 1 minus 1 by omega square L c. Now, writing omega naught square is equal to 1 by L c, we find that Zin can be written as R plus j omega L 1 minus omega naught square divided by omega square. So, omega naught is the resonant frequency, because whenever omega is equal to omega naught, the imaginary part of the input impedance becomes 0 and Zin becomes purely resistive. We should note that for a series RLC circuit, the real part of Zin, this is constant R, and the imaginary part of Zin below resonant frequency omega naught, this is capacitive, and above resonant frequency omega naught, it becomes inductive. So, if we plot the imaginary part of Zin, and here at omega equal to omega naught, the resonant frequency, the imaginary part of Zin becomes 0. We can write magnitude of Zin as a function of omega as under root r square plus omega square L square 1 minus omega naught square by omega square whole square. And if we plot magnitude of Zin omega, then we find that from this expression At omega equal to omega naught, magnitude of Z in omega becomes minimum and equal to R. For other values of omega, magnitude of Z in omega is greater than R. And we have marked this horizontal line where it becomes R by 0.707, that means root 2 R. This particular points, see, we will relate it to half power bandwidth of the resonator. An important parameter of resonant circuit is its Q, which is defined as Q is equal to omega average energy stored divided by average power dissipated. This parameter Q is called the quality factor, and therefore, we can write Q is equal to omega W m, the energy stored in magnetic field, plus W E, the energy stored in the capacitor. This is the energy stored in the inductor W m. So, sum of these two energies, it gives the total energy divided by P loss. The loss happens at the resistance R. Now, at resonance, that means when omega is equal to omega naught, W m becomes equal to W e, and therefore, we can write Q can be written as either omega naught 2 W m by P loss or omega naught 2 W e by P loss, you will see. And the Q of a resonator itself, disregarding external loading, that means we are assuming that no external load is connected to this resonator, whatever Q that we are getting, that is within the resonator itself, that is because of the losses within the resonator itself, and this is called unloaded Q and denoted by Q naught. So, therefore, Q naught is omega naught 2 W m divided by P loss, and when we substitute the term related to the energy stored in the inductor and the power loss or dissipation in the resistor, then we get Q naught equal to omega naught L by R, and since omega naught square is equal to 1 by L C, we can also write Q naught is equal to 1 by omega naught R C. We can substitute L to be equal to 1 by omega naught square C, and then we will get this term. Now, let us study the behavior of the input impedance of a series RLC circuit or a series RLC resonator near its resonance frequency. So, this expression Z in is equal to R plus j omega L omega square minus omega naught square divided by omega square, that we have already seen. So, what we can do in the vicinity of the resonance, we can expand this term omega square minus omega naught square is equal to omega minus omega naught into omega plus omega naught. Now, we write omega minus omega naught as delta omega, and when we are very close to the resonance, omega plus omega naught can be written as 2 omega, and therefore, small delta omega we can write Z in is equal to R plus j omega L into 2 omega delta omega by omega square, which becomes approximately equal to r plus j 2 delta omega L. And if we substitute from here L equal to r q naught by omega naught, then we get approximate expression for Z in, which is given by r plus j 2 delta omega r q naught by omega naught. Now, this form of representation of the input impedance near its resonant frequency, this expression is a very useful expression, and we will make use of this expression in our later analysis of transmission line resonators. Let us now consider half power fractional bandwidth of the resonator. Now, we have P in is equal to half V I conjugate, which can be written as half Z in V by Z in mod whole square, and therefore, the real part of P in becomes real part of Z in is R. So, half R V by Z in mod square, and when omega is equal to omega naught, we have seen that Z in is equal to R, and therefore, real part of P in at omega equal to omega naught, this becomes equal to mod V square by 2 R. And if you remember, we have seen that mod Z in, we marked a line when mod Z in becomes equal to R by 0.707, that means root 2 R. So, mod Z in square at those frequencies become 2 R square, and when mod Z in square becomes equal to 2 R square, the real part of P in becomes half of real part of P in at omega equal to omega naught. So, that is why these frequency points are called half power points, and in the plot shown we see that we have two such points, one below omega naught and one is above omega naught, and from this expression Z in is equal to R plus j 2 delta omega R q naught by omega naught. We can find the modulus of Z in square, and this becomes R square 4 delta omega square R square q naught square by omega naught square, and we can equate this to 2 R square. So, once we do that, we will get, if we can take out R square common from here, then R square will get cancelled from both sides, we will be left with 1 here, and when it is subtracted from here, then we will get 4 delta omega square q naught square by omega naught square is equal to 1, and therefore, we can write 2 delta omega by omega naught whole square is equal to 1 by q naught square, and this quantity 2 delta omega by omega naught, this quantity we defined as fractional bandwidth, and therefore, we see that the fractional bandwidth is given by 1 by q naught. So, higher the value of q, the fractional bandwidth will be narrower, and we have seen that q naught is given by omega naught L by R. So, if R increases, the power loss in the circuit increases, Q will decrease and we will have larger fractional bandwidth. Whereas, if R is very small, then Q naught will be large and fractional bandwidth will be very small. So, for a highly tuned circuit or a very narrow band resonator, we will have large value of Q naught, and for that we will have R to be very small. Let us now consider the properties of parallel RLC circuit near its resonance. So, the parallel RLC circuit is shown in the figure. For this type of a circuit, we can write Zin is equal to 1 by R plus 1 by j omega L plus j omega C, and this can be written as 1 by R minus j by omega L 1 minus omega square L C. Now, we can find out the real and imaginary parts of Zin if we multiply the numerator and the denominator by the complex conjugate of this term. Now, real Zin will attain its maximum value R at the resonant frequency, and at the resonant frequency the imaginary Zin will be 0, and this resonant frequency is given by omega naught, which is equal to 1 by root L C. Now, these plots show the roughly the nature of variation of real part of Zin and imaginary part of Zin with frequency, and we see that for a parallel RLC circuit below the resonant frequency omega naught, it will be inductive in nature, and above omega naught it will be capacitive in nature. In a series RLC circuit, we saw that below resonant frequency omega naught, the circuit behaves like a capacitive circuit, while above resonant frequency it is an inductive circuit. Now, Q naught, the unloaded Q factor for such resonant circuit, can be found out, and Q naught will be equal to omega naught R C, and which is also R by omega naught L. Near its resonance, the frequency, angular frequency omega can be written as omega naught plus delta omega, and Zin, once we substitute omega is equal to omega naught plus delta omega, can be expressed in this form. And if we plot the variation of magnitude of Z in with respect to omega by omega naught, then we will have the maximum value of the magnitude of Z in at omega equal to omega naught. That means, when this ratio is 1, and we will see that half power points will be for magnitude of Z in omega to be equal to 0.707 of its maximum value, that is r. Now, this term we can do some approximation, particularly because of the fact that delta omega by omega naught is very less as compared to 1 when we are operating this circuit near the resonant frequency omega naught. So, what we can do, this term 1 by 1 plus delta omega by omega naught, this can be approximated as 1 minus delta omega by omega naught. So, once we substitute this approximation, then we get Z in to be equal to 1 by r plus j omega naught c plus j delta omega c plus 1 by j omega naught L minus delta omega by j omega naught square L, entire thing raised to the power minus 1. Now, this is the form of Z in we have seen, and these two terms j omega naught c plus 1 by j omega naught L, when combined, it will give 1 minus omega naught square L c, and therefore, these two terms will cancel out. So, we find that this j omega naught c and 1 by j omega naught L, when combined, they will give term like 1 minus omega square L c, and therefore, it will become, sum of these two terms will become 0, and we will be left with Z in equal to 1 by r plus j delta omega c plus j delta omega by omega naught square L whole raised to the power minus 1. Now, once we substitute omega square is equal to 1 by L c here, we will see that this term j delta omega by omega naught square L will reduce to j delta omega c, and therefore, Z in can be written as 1 by r plus j delta omega c from here and another j delta omega c from here whole raised to the power minus 1, and therefore, it can be written as r divided by 1 plus j 2 delta omega r c. Since we have q naught is equal to omega naught r c, therefore, we can now write Z in equal to r divided by 1 plus j 2 delta omega q naught by omega naught. So, this expression of input impedance, it gives the input impedance of the parallel resonant circuit near its resonance, and you can see that this expression also includes q naught, the unloaded q factor, and also omega naught, the angular resonant frequency. Now, let us develop the expression for the fractional bandwidth. From the parallel RLC circuit, we see that real part of P in input power is equal to half V, the voltage, it is a parallel RLC circuit. So, the voltage will be same across all the elements. So, it is half V, V by R conjugate, and V by R is essentially the current through the resistance, and therefore, we can write it half mod V square by R, and which is equal to half I square mod of Z in square divided by R, because V is written as I into Z in. Now, at resonance, that means when omega equal to omega naught, real part of P in becomes equal to half mod of I square R, because we have seen that at omega equal to omega naught, mod Z in become equal to R, and therefore, we can now write real part of P in divided by real part of P in at omega equal to omega naught. This can be written as mod of Z in square divided by R square, and for this quantity to become half, because we are talking of half power bandwidth, we must have R square by 2 equal to mod of Z in square. Now, we already have an expression for the approximate input impedance of the parallel RLC circuit near its resonant frequency, and therefore, we can write from Z in is equal to R divided by 1 plus j 2 delta omega q naught by omega naught. From this expression, we can see that mod Z in square will become R square by 2 when we have 2 delta omega q naught by omega naught is equal to 1, and the fractional bandwidth is given by 2 delta omega by omega naught, and therefore, once again we find that just as the case of series RLC circuit, the fractional bandwidth 2 delta omega by omega naught is equal to 1 by q naught. That means, for higher q, the fractional bandwidth will be very less, and for lower q we will have larger fractional bandwidth. Now, so far we were discussing about q naught, the unloaded q. Let us now consider another form of quality factor, which is called the loaded q. The unloaded q of a circuit, q naught, is the quality factor of the circuit without any external loading. In practice, external circuitry that will be connected to the resonator will produce loading effect. And let us see how we can take this loading effect into account. Let us represent the loading of the external circuit by a load resistance RL and Q of the external circuit by QE and QL be the Q of the loaded circuit. Now, when we consider series RLC circuit, our external resistance RL will come in series with the resistance of the RLC circuit R, and therefore, the effective resistance will be R plus RL, and therefore, by definition of Q, we can write QL, that of the loaded circuit, is equal to omega naught L divided by R plus RL. If you write 1 by QL, then it becomes R plus RL divided by omega naught L, and this term R divided by omega naught L can be written as 1 by Q naught, and RL divided by omega naught L can be written as 1 by QE. So, the Q of the loaded RLC series RLC circuit 1 by QL is 1 by Q naught, the unloaded Q, plus 1 by QE, the Q of the external circuit. Let us now consider the parallel RLC circuit. In case of parallel RLC circuit, the external resistance RL will come in parallel with R, and the effective resistance will now be R into RL divided by R plus RL, and therefore, for a parallel circuit, QL can be written as R RL divided by omega naught R plus RL into L. And if we write 1 by QL can be written as omega naught R plus RL into L divided by R RL, and when this is separated, then we will get omega naught L by RL, which is 1 by QE, plus omega naught L by R, which is 1 by Q naught. So, once again we find that for a parallel RLC circuit also 1 by QL is equal to 1 by QE plus 1 by Q naught. So, once we know the unloaded Q of the series or parallel RLC circuit, and we know the external loading, that means RL, we can find out the Q of the loaded circuit. So, we have studied series RLC and parallel RLC circuit, and particularly how such circuits behave near their resonant frequencies. Next, we will see how transmission line sections, either short or open, can act as resonators, and also near the resonant frequency how we can model this type of transmission line resonators by equivalent RLC circuit.